and welcome everybody to another PWI Lunch and Learn session. My name's Phil Kirkland, Vice President North for the PWI. I trust you all had a good Jubilee holiday break, and now we're back into business, so we'll move on with today's presentation. A few housekeeping rules before we start. If you could turn your mobile phones off, please. Switch your cameras off, switch your microphones off, and use the chat room for any questions, the chat room function on your screen, and we'll have a Q&A session towards the end. It's my pleasure today to welcome Professor Roger Lewis from Sheffield University. Roger is currently Professor of Mechanical Engineering.
Lost you, Phil.
Oh, I'm glad it wasn't just me.
Try turning your camera off to give you more bandwidth. Hey Roger, we seem to have lost him, so if you want to start your presentation.
Okay, well, thank you very much for the introduction, what we heard of it, and thank you very much for the invitation to speak today. I'm going to be talking mainly about some work we've been doing, developing a new way to clean railhead to overcome the problems of low adhesion. But at the beginning of the talk, I'll give you a little bit more of a flavour of some of the other work we do on low adhesion, right from the sort of fundamental end through to application. So a quick outline, bit on our work on low adhesion.
Sorry about that, Roger. Yeah, my internet connection dropped out at this end, but it's back on.
Okay.
Yeah.
I've made it.
Yeah, off you go then.
Yeah, sorry. Yeah, so I'll cover a bit about a wider range of low adhesion work initially, and then move on to what we're doing with our railhead cleaning technology, a bit about the actual process, how we developed it going from lab to field, and then some examples of how it's been used on track in some different scenarios, and then what we're doing in the future to take this further forward. So at the moment we have a strategic partnership with the Rail Safety and Standards Board that's co-funded by the Royal Academy of Engineering, and it's all centred around understanding and management of low adhesion in the wheel rail interface. So at the very low TRL or RRL level, we're looking at understanding fundamentally what's happening when there is contamination on the railhead, and how this influences friction levels in the wheel rail interface. This is quite multidisciplinary. There's a lot going on both physically and chemically within the wheel rail interface. And it's the chemical reactions that are driving the low adhesion mechanisms, whether that be due to leaf material being present or wet rail where you have oxide mixing with a small amount of water to form a slippery paste. Now, obviously, understanding the fundamental mechanisms then helps us to define and develop better mitigation methods, hopefully. Maybe things that can be used proactively to stop the contamination layers that cause a low adhesion forming, or in terms of dealing with them once they do exist. So that's a lot of what we do in the laboratory, but we've got a number of examples of where we've taken work out of the lab and started to turn it into tools and technologies that can be used by engineers working in the railway industry. Apart from the kind of lab work we do, we're also doing some modelling. So we have a couple of modelling approaches for predicting friction levels in the wheel rail interface. One of those I'll talk a bit about in a further slide, but here the machine learning approach, this is all based on images taken of well, forward-facing images from a train and railhead images, and through training neural networks with measured friction data from the field associated with pictures, we developed a tool that will allow you to predict friction levels using the images. We're just about to put a camera on a train this autumn to take that forward, but more about that at the end, because the aim is to try and tie this in with the cleaning approach to make the cleaning smarter. Most of what we've done in terms of implementation is our cryogenic railhead cleaning approach. So I'll put more of that in a bit. So at a fundamental level, we've been looking quite closely at which bits of leaves cause low friction. So we did some work on tannins, which I guess most of you will have heard about in the context of tea. So we actually created some leaf tea with a bit of rail steel in there, because the role of oxides from the rail steel is quite strong. So you can see here we carried out some twin disc testing, so that kind of rig allows us to simulate wheel rail interface conditions, contact stresses and slip values. So we drip our leaf tea in and we can measure friction on this rig. If you look at the graph, you can see the blue box is what happens when you have just water in the contact. Then the orange bar is what happens when you use the leaf tea, and you can see friction levels getting down to 0.05. This is what we'd define as ultra low. You're definitely going to have braking problems and traction problems at that level. Just to put that into context, the highly formulated lubricants that you'd put into a car engine would probably only deliver about 0.06 typically. So leaf mixtures are very, very lubricating. So the green bar on the right hand side, this is actually the leaf tea treated with a chemical to suppress tannins. So this is the tannins removed. So you can see we've found some quite strong evidence that the tannins within leaves are helping promote the low friction. That's just one aspect of the kind of friction mechanisms you get in the wheel rail interface, though, when you have leaves present, as there are many other ways they can cause the railheads to be slippery. Just the physical presence of the leaves creates the kind of low shear behavior that would lead to low friction, although it is very important that they're wet. If you have a dry leaf layer, it's a lot less of a problem. This is the other low friction model that we've been working on in collaboration with the University of Huddersfield and Virtual Vehicle. Initially, we built a model looking at wet rail, so what happens when there's oxide within the contact, and then we extended that to look at leaves using the full-scale Harold rig at the University of Huddersfield. So you can see here we created some leaf layers on the wheel and rail, and in fact the role of the wheel in this problem shouldn't be underestimated. I think it's something that's been ignored, because we see the leaf layers on the railhead, and obviously they are quite influential, but leaf layers are also created on wheels, and of course the wheels can carry the problem further than they might exist on the railhead alone. You can see here on the top graph some of the friction levels we measured on the Harold rig, and then here we're getting even below 0.02 under some conditions, so incredibly low friction. So we carried out quite a large series of tests which allowed us to parameterize a model, and that enables us now to produce creep curves for different wheel rail interface conditions with different levels of contamination. And there's a little GUI here that allows people to set those conditions and then create a creep curve. Those creep curves are useful on their own to see what the main influences are on friction, but they can also then be put into multi-body dynamic simulations, so they can be used to study train performance in the kind of modelling environment under low adhesion conditions. They've also been built into the Labrador train braking model, again, which the University of Huddersfield have developed. So look at what braking strategies you might be able to use to try and overcome the low adhesion conditions. So that's a little bit of some of the other work we've been doing on low adhesion. There is quite a bit more, but the main subject of the talk today was our new cleaning technology based on the application of dry ice pellets and how we're using that to clean the railhead. So our overall aim is to try and develop a new cleaning approach that can be deployed in a variety of configurations. This is quite important, particularly in the context of the problems that there have been with railhead treatment trains over the last few years. Not least of all the fact that they can only do a one-hit clean, but of course getting them out onto all areas of the track where there are low adhesion problems is difficult. So our ultimate aim is to try and develop a system that could be integrated into a passenger train, and through doing that provide a more frequent clean, but it can be a less powerful clean as well. So we're stopping the contamination as it's building up, and so allowing it to get to a really high level where problems may occur. However, we're looking at different operating scenarios for the cleaning, as you'll see as I go through. So first of all, how does this work? So we're firing dry ice pellets, so through a nozzle onto the railhead. So these pellets come out in a stream of air going at supersonic speed. So they have quite a lot of kinetic energy when they hit the rail surface. They're very cold, so they embrittle the coating, and they sublime once they hit the surface. So they turn back to a gas in a tiny fraction of a second, and you get around an 800% increase in volume as that happens. So you've got kind of three mechanisms combining there to enable the whatever contamination layer you've got on the surface to be removed. Many benefits to using this kind of approach. Obviously, there's no residue. There's no impact on the rail or any of the other track infrastructure. This means they can be used more widely and go over things like S&C. And of course, we've got quite a flexible application approach. So we can vary the flow rate depending on how contaminated the track is. We can have a number of nozzles as well. I guess the biggest thing is that we can squeeze the technology into a much smaller volume than can be achieved with perhaps the water jetting, for example, that's currently used. So we could get this onto a single vehicle or miniaturize it to put it onto a passenger train. So a bit here about the development process we've gone through. We started off in the lab in a small RSSB funded project where we were able to show that application of the pellets increased traction in a very small amount of time when you had a contaminated twin disc contact. And from there, we've kind of scaled up through a number of different cleaning platforms, gradually increasing the speed that we're able to test at to really prove that this will work live on the network at the kind of speed a railhead treatment train may need to go at, so about 60 miles an hour, but also on a passenger train traveling around the network. So initially on a road to rail vehicle, this is a trailer mounted system, so we're limited to 10 miles an hour because that's how fast the vehicle is allowed to go. Then moving on to the NEXUS Tyne and Weir railhead treatment train, a bit more about that later. And from there, testing on passenger trains, initially on a freight branch line near Sheffield, and then moving on to very recently where we've tested live on the network. We've gone back to the Herald rig again because we've developed a method for creating leaf layers. We've gone back there to see how best to apply the dry ice at high speed. So we're able to both create the leaf layers, clean them off, and then carry out brake tests on the Herald rig. We're also able to simulate the cleaning you might get from a railhead treatment train version, so a one-hit clean, and also a more frequent lighter clean to see what the impact would be. We've also been developing a dry ice pellet generation system that fits inside that small cabin you can see there. In fact, it doesn't really fill that, so it could be much smaller than that. So that this means that we effectively have a system to generate the pellets on the go, which could go onto the back of an MPV, for example, along with the blasting units. So the very first test we did, moving out of the laboratory, were actually we went directly onto a vehicle. It was a Class 117 vehicle at Long Marston. We created our own leaf layers, as you can see, only 3 meters long, but this was enough to give us a very big change in braking distance, as you can see here on the graph. So we kind of created this easy to implement low adhesion layer to try our cleaning out on. We did a number of different trials, sort of cleaning the leaf layer off with a separate vehicle, but also applying the dry ice directly from the Class 117 vehicle, both before or during braking as well. We tried all sorts of different scenarios. Here's an example of some of the data that we got from that. So you can see here we've got deceleration, and we went round on a number of loops. So it's a looped track at Long Marston. We created our leaf layer. Before that, we did some dry braking, which you can see there's a blue line. Then with the leaf layer, you can see much reduced deceleration on the orange line. Now the grey line shows what happens when we did our loops applying the dry ice. So initially on the first 2 loops on the grey line, we were just braking on the leaf layer. Then on loops 3 and 4, we applied the dry ice pellets, and you can see our braking is back up to dry conditions. And then the final loop, we switched it off again. So a little bit of a reduction, but here we weren't aiming to clean the layer. We were looking to improve the conditions in the wheel rail interface while we were braking. So that looked very promising. From doing that work, we kind of decided that the cleaning approach was probably the one that was going to be closer to market, rather than immediately trying to develop a system that might replace something like sanding, for example, which is going to be very hard to do within the rail industry. So we developed a smaller system that we could put onto a trailer to be towed by a road-to-rail vehicle. We did an initial trial in 2019 across 5 different sites in the UK, sort of very short trials, 2 or 3 days. And then in 2020, we cleaned on the West Highland line in Scotland for the whole of the autumn period. So we put in place an ice pellet production facility because it was quite remote. We couldn't get them delivered. Typically, you can get them delivered quite quickly if you want to, same day. But to ensure our supply, we built our own generation facility. Here we were trying to move on from the short-term trials to show that it was a reliable approach, and would consistently clean throughout an autumn period. And we also were working on making sure we could clean the whole of the railhead. That's obviously quite important. And some of the other cleaning approaches have quite a narrow cleaning width, but we've got up to 40 millimeters now, so we can clean across the whole railhead. So that's ongoing. This kind of system is ready to be used and implemented. Shortly after that, we had a first of a kind project where we were lucky to be able to work with the team at the Tyne and Wear Metro, who have their own railhead treatment train, which usually is operating a kind of water jetting system, but also applies some traction gel as well. But fortunately for us, there was enough space on the flatbed wagon, which is built on to put our dry ice equipment on. So we developed a system for going out on operational cleaning runs. On those runs, which were carried out in 2020, the water jetting was turned off. We did have some video monitoring of what was going on, so just in case anything failed, the water jet could be switched back on. But fortunately, everything went very smoothly. You can see here, this was a stop at a level crossing, I think. You can see there's a dark rectangle there. Well, that is the cleaned portion of the railhead. So you can see it was removing whatever contamination there was on the railhead at that point. We're quite lucky that NEXUS keep a good record of their delay minutes, and you can see in the days where we were cleaning, Certainly on 3 of them, we got the delay minutes down to very low values. On day 2, there was a bit of a problem. There was nothing to do with low adhesion that pushed the numbers up, but quite a big reduction on the weeks preceding that, which aren't shown here, but also on previous years as well. So looked very promising for the approach. Within that same project, we did a short trial on a passenger vehicle with Northern. So this involved fitting our equipment to a Class 155 train. There's actually a branch line quite near to Sheffield, which is a freight branch line going to a glass factory. It only has about 3 trains a week taking sand to the factory, but it's got a lot of vegetation. So it has leaf layers, quite heavy leaf layers, even in March, typically, and maybe all year round. So obviously we were quite delayed in this work due to COVID, which pushed back the trials to March. But fortunately, there was still quite a lot to be cleaned off even at that time. So you can see here on the images on the right, this is what the railhead looked like before we cleaned, and this is below what it looked like after cleaning. So you can see, again, very heavy leaf layer, and lots of leaves around still, even in March, which is quite good for us. It's a good test location. We did record what that was doing to the stopping distances. We're able to get up to 40 miles an hour in this testing. That was about the limit for the line. It's quite hard to find places where they'll let us go much faster than that, which is what we've been working on since this project. But yeah, again, you know, we were finding that the cleaning was effective, and this was not that railhead treatment train big blast. This was a lighter blast carried out over a number of passes before we did the brake test. So, following on from the first of a kind project, we had some performance innovation fund investment, which has allowed us to take slightly different train, Class 153, out onto the network with our equipment on board. We haven't reached a point yet where we've been allowed to put the equipment under the train, although it can be packaged to a size where it will fit under the train, and that's what we'll be working on as we move forward. So again, we took this system to Bretton, where we carried out some tests again on some very thick leaf layer, again even heavier than the previous time. You can see it's working to clean it off. That kind of gave us the sign off to go out onto the network with this new prototype. So we cleaned over a number of nights on the route you can see here from Holbeck to Wakefield, Kirkgate. We're doing a number of loops. We're cleaning at line speed and prioritizing the positions just before and after stations, where obviously a lot of more problems are likely to occur as trains are braking and trying to accelerate. We were unlucky in a sense that the railhead condition that night on those nights was actually not too bad, and this is a problem with trialing all of this kind of technology. Actually, we'd really like the testing conditions to be awful, but of course you can't ever let them get to that state on the live network. So other mitigation can't be switched off just so we can try our system. We've got some good data coming from the measurements, and also some very good anecdotal feedback from the drivers who were noticing a difference in the braking performance post cleaning. So in parallel with that work, we were carrying out some testing on the Herald rig, which is the big full-scale rig at the University of Huddersfield. Essentially, it involves 2 big loops of rail over which you can position a bogie, and we can carry out tests where we build up a leaf layer, as you saw earlier, and then you can do a brake test, which allows you to establish a friction level. So we carried out a number of different types of tests on the Herald rig. So we're generating the leaf layer, initially on the wheel and rail. We were then moving the wheel away, and we did some wheel cleaning tests. As I said, the wheel is quite an important part of this problem, and wheel cleaning might be something that can be looked at in the future. I know we've done some tests. Well, we did some tests in this study as well, looking at the use of Citrosolve, which is being used in Scotland at the moment. So it's being sprayed onto wheels of trains coming into depots to try and help remove any contamination layers on the wheels. So once we had our clean wheel, we then put it back over the leaf layer. So we did some brake tests with the leaf layer there, but then also on the rail leaf layer post cleaning, either with our kind of passenger train system approach, so low power frequent clean, or a railhead treatment train type clean, so a high power one hit clean. And then we also tried applying the dry ice during the braking on the leaf layer. The leaf layers created were very severe in this instance, so you can see an example there of quite a thick leaf layer. It certainly corresponds to the highest rating on the Network Rail classification. And when we did the cleaning, we cleaned at 60 miles an hour. After that, we carried out brake tests at 10 miles an hour or 60 miles an hour. So a number of different things we were looking at here. First of all, just some images of the leaf layer. So here on the left, sort of just after creation, you can see the dry ice application then on the rail in the middle, and how it leaves the railhead post cleaning. So pretty much within the cleaning band, everything's been removed. That middle one shows the kind of passenger train approach, and then the one hit with the railhead treatment train post cleaning. So really good removal. But what impact does that have on the braking performance? So what you can see here are essentially creep curves measured during the braking. So the important part of this curve is the top part. You can see here data for both dry, in the main graphs, the dry leaf layer friction, which is quite low, but not ultra low. If you remember back to the wet leaf layer measurements we took in developing our LILAC model, we were getting below 0.02. So post cleaning, you can see that the creep curves are pushing friction up above 0.1, which is about the threshold for good braking, and that's both at braking at 10 miles an hour and 60 miles an hour. So a big change in friction over that kind of very low 0.02, getting up to 0.1, 0.2 in some instances. Remember, this is much higher speed cleaning than we'd achieved in any of our other testing. So good evidence of the leaf layer being removed, and a good increase in the braking performance as well, both for the passenger train variant and the railhead treatment train variant. And we saw the same as well when we were applying the dry ice while braking. So this is not on a cleaned rail, this is on a contaminated rail. So we're actually applying the dry ice during the braking event. And again, we're getting friction levels approaching 0.15. So that's good. I would say at the moment we're not putting this forward as a technology to try and replace sanding. I think the rail industry has good confidence in sanding. This is a way to clean the railhead from a passenger train during operation, to try and reduce the need for railhead treatment train use or any other cleaning approaches. Onto the wheel cleaning. So as you remember, I said we moved the wheels away from the rail, and then we rotated them slowly while cleaning with the dry ice. So you can see here a very thick leaf layer on the wheel. But you can see here post cleaning we've managed, and that is just one pass of the dry ice. We managed to remove most of the contamination. Now, I'd say most wheels are not going to come into depots looking in this state, but certainly during autumn they're likely to have some level of contamination on them. And maybe cleaning wheels is another good way to look at reducing the problem of low adhesion. So where does that leave us at the moment in terms of our technology? Well, we've got a couple of road-to-rail vehicle systems, one based on a trailer, which you saw earlier, but we've also run a system on the back of a Unimog. Because that doesn't involve the use of a trailer, we can go up to 20 miles an hour, which obviously gives quite good speed increase. We've got our own pellet manufacturing system, so this could be something that's used on board a train, but certainly can be a system that can be put in a depot somewhere to manufacture pellets for use on road-to-rail vehicles or treatment train systems. So yeah, very successful trial with NEXUS on their railhead treatment train. That system's still sitting there, ready to be used again in the future. But now our main focus is on developing our kind of passenger train variant. So we've run it on the network at 60 miles an hour, but we've got a couple of projects now that are going to take that forwards. They've been enabled largely by the fact that we've bought 2 railway vehicles ourselves. So University of Sheffield now owns 2 trains. We got kind of fed up with trying to borrow vehicles from other people because naturally they're a little reticent to let their vehicles go because they need them. But there are all sorts of other issues around us making adaptations to trains, as I'm sure you're all aware of, and then running tests. So the plan is with our 2 vehicles to set them up as cleaning demonstrators as part of 2 more PIF projects that we've got running through to early 2025. So these are going to be stored at the Wensleydale Heritage Railway, where we will be able to run some tests, but of course that has a link to the network as well, and these trains will be maintained ready for network use. So in one of the projects, again in collaboration with Northern, we'll be developing one of the trains to basically be a railhead treatment train units that can be used for service cleaning. Has a number of benefits over a railhead treatment train, as I've mentioned earlier, not least of all that it can go to a lot more places more easily. Also, part of that project will be developing an under train version of the passenger train system, again to demonstrate that we can achieve that, and then how effective it will be on cleaning. In a separate PIF project, this is with Network Rail in Scotland, we'll be looking to integrate the under train cleaning system and our machine learning technique for predicting friction on the train. So this autumn we'll be trialing the camera units and the friction prediction aspect to try and benchmark the friction conditions on the route where we aim to clean the following year when we've got the under train cleaning system implemented. This will help us to make the cleaning process smarter. We don't really want to be cleaning all of the track when it doesn't need it, but if we got a system that can recognize where there are low adhesion conditions, this will help us optimize the consumable bit more, or the consumable use while we're running. So quick summary. We've shown that our cleaning technology can effectively remove all different types of contamination, oxide and leaf contamination, and quite severe leaf contamination as well. And we've shown both in field measurements, in brake tests, and within the lab on the Harold rig that this can make a big improvement to braking performance. The technology is very flexible. It can be implemented. It can even be implemented on a push trolley. We have done some trials with Northern on a push trolley for cleaning, but then stepping up onto road-to-rail vehicle, railhead treatment train, and now demonstrated on passenger trains, well actually up to 60 miles an hour now. And of course we've cleaned on the Harold rig at 60 miles an hour. So we're crossing those required speed thresholds from Network Rail, but also obviously cleaning on a passenger train, we need to be able to clean at the line speed, which may be in some cases over 60 miles an hour. In terms of our consumable, it can be delivered. There is a very wide dry ice pellet distribution network because they're used quite extensively in food delivery, so on trucks where cooling is required, but also airports have their own dry ice manufacturing facilities, often because they use the pellets for keeping food cool on planes. So we've got good control on our cleaning power. We can cover the whole of the railhead, and we're taking it forward now onto passenger trains for further network trials on systems mounted under the train, but also developing our own railhead treatment train unit as well for deployment. So we've worked with a lot of people on developing this, and they've all been very good to work with and very supportive. And obviously we'll be still working with quite a lot of them as we go forward. Just a little note to say there are some videos which I wasn't able to show today because of bandwidth issues of the system. So if you go to that website, you can have a look. They send you through to links to YouTube videos of some of the work we've done on NEXUS, but also at Bretton with Northern Trains. Okay, thank you very much.
Thanks, Roger, for a fascinating presentation. It's open to questions now. If you can pop them in the chat room. I'm not seeing any on my screen yet. Has anybody put any questions up?
Yeah, people can also raise their hands in Teams.
Sorry, Sarah, I didn't quite catch that.
There's no chat yet, but people can always raise their hands as well in Teams if they want to open their mics up.
Yeah. Yeah. Anybody like to ask any questions? If you could give your name and PWI section or employer when you ask the question. It's all very quiet. On a personal note, Roger, I was very pleased to see the use of the railhead treatment train at NEXUS, something I fought for several years. Any update on whether it's going to be put into full use this autumn yet?
No, I think there's been obviously there's been a bit of a distraction with the introduction of the new fleet and the building of a new depot. We're keeping our conversations going. I think maybe when all of that's settled down, we'll be in a better position to go and do something. But of course, funding is also an issue as well. I think obviously COVID's had a big impact on the railway industry and reduced its ability to start investing in new innovation, which is a bit of a shame. The impending strike is causing us a few problems as well. We've had one project cancelled for this autumn just because of a potential lack of people available to implement. So I think there's a bit of caution being exerted.
I mean, the delay minute figures were pretty impressive, I have to say. Yeah,
actually, I mean, that one of our big problems in testing this kind of technology is getting data like that really shows that it's working, because we can measure friction levels, we can measure braking distances, that's fine, but actually the industry wants to see an improvement in performance, and the measures of that performance are things like delay minutes. But it was quite good because that's kind of a closed network. It's a bit easier to get that kind of information. We really struggle with that on other routes because there's lots of other causes of delay minutes, and trying to sort of extract the important bits that show what you've done is actually really difficult.
Yeah, okay. Any other questions, please? No, it seems to be silence out there.
That's okay. People free to email me if they want to know any more or have any questions they don't want to ask now. quite happy to
Yeah,
field them later.
I really appreciate that, and I'm sure as we go forward, the presentation would go down well at section meetings, section presentation. It's very interesting. So if there's no more questions, I'd like to thank you for your time, Roger.
Yeah, no problem.
Thank you for supporting the PWI with another fascinating lunch and learn session. And with that, we'll close today's session. Thank you very much.
Thank you.